Ever since we launched Titan, I've been looking forward to doing a technical walkthrough video where we can go through all of the cool features and functionality that we built into the stabilization ecosystem that distinguish it from the rest of the competition. Thanks for joining me. I'm Zach from MotoCrane, and today it's all things Titan technical, going from the transport case to the deep dive into the controller, building payloads, and everything in between. This video is here to make sure that you are off to a great start using Titan on your sets. So opening the Titan transport case, we see that there is a top tray here that includes space for everything included in the Titan Ultimate bundle. At the bottom right here on the top tray, we have the Airy style dovetail, as well as a bridge plate and 19mm rods. Of course, that's for attaching to our payloads. We have a hard copy of the Titan operation manual, and then underneath that is our Titan controller. There are no input modules yet installed in this. In the middle, we have lens control motor cables, and then we have our male Mitchell mount adapter, as well as a brass male Mitchell nut. Underneath that, we have all the tools and hardware needed, as well as some safety hooks that can be installed for when you're operating over people and you want to safety latch the gimbal to whatever support structure you're using. And then, like I said, the controller doesn't come with any of the input modules installed. These are all sitting right here, so you can configure the controller to the preference of your operator. You have common dual axis joystick here, as well as two single axis options as well. And then the focus control knob as well here. In case you're controlling Titan wirelessly, those are antennas that we'll install in a second here, so you can see how those go on to the wireless radio modules. And then we have 3 lens control motors here, which come installed with the 0.8 pitch gear on it. And then we have the camera top lock rail. This gets installed onto the top of the payload for really secure attachment to the Titan camera cage. So then we also see that there's these 2 straps here as well, and that allows us to lift this straight up and out of the case and see Titan underneath in its sort of main compartment down here. Titan is in a packed position. Right now you can see the IMU housing is popping up, and we saw that there was a cutout in that top tray, so that's how that gets packed. And then we have 4 main cables that are used with Titan: power and the comm cable in 2 different lengths in both 25 and 50 feet. In these 2 cutouts, we have Titan carrying handles. These use common 3/8 inch thread, and you can install them on either side of the Titan pan housing like this. And this makes it a lot safer and easier for operators or technicians to carry the gimbal in and out of the case, as well as to and from any kind of camera support as well, while you're attaching it to the end of a techno or supporting it while it's getting mounted up. So those just can get threaded on and off really easily, and they go right back into that hole. So that's the Titan transport case, and now we'll get into the Titan wheels case. So the Titan wheels come in their own custom SKB case, and when we open it up, we can see that there's spots for 3 wheels modules. These come pre-installed with brass if they are ordered that way, and then there's also the aluminum wheel as well. And then finally over here, we have all the associated cabling with wheels, which is what connects the first wheel to the controller, and then shorter ones for daisy chaining additional wheels off of that one. In this cutout right here, we include all of the parts for mounting the wheels. We call this part the battle station, which is used for mounting the controller, as well as the wheels to a support structure like a Mitchell-based tripod, Ronford Baker sticks, that kind of a thing. You also have a lot of 3/8 and 1/4-20 threaded holes for mounting this part to a lot of different things like tracking vehicle interiors, etc. And then at the bottom, we have that hardware for, again, attaching this to a Mitchell base. We also include standoffs for increasing the spacing between the battle station and the Mitchell base as well, depending on the configuration of the wheels and what kind of space you require for your application. So building a payload for Titan is going to be a very familiar practice for those that have built anything onto an Airy dovetail. We're going to go through that process here just to make sure that the best practices are applied and that the payload is built with maximum end-to-end stiffness, which will make sure that our tuning is optimal and that we get the best performance out of Titan. So I'm going to start by grabbing my bridge plate and my 19mm rods from the Titan transport case, as well as all my hardware and tools that are included. So I've got my bridge plate as well as 19mm rods installed, and this bag of hardware that's used for attaching bridge plate to cameras. So I'm going to pull out my rails and then get this bridge plate installed onto this Komodo X that we're using here today, and then we'll get our lens installed. I'm just going to loosen my rod clamps here, and then we can pull these rods, just so they're not in our way for this stage of the build. set those aside. And then I'm gonna take our Komodo X here, and I also have a nice spacer here from Wooden Camera, which gives me proper studio spacing for the lens. I'm gonna tip that upside down so that I have my threaded holes exposed. And then get my bridge plate here roughed over the center. Now within this hardware bag, we have both 1/4 as well as 3/8 threaded tripod screws, which will go into this slot here and secure the bridge plate to the bottom of the Komodo. So I'm gonna get these 3/8 screws installed between the bridge plate and the payload. Just gonna install them here, which makes them captive inside this slot. Do that again for the second one. There's 2 3/8 threaded holes on the bottom of this payload, so it's an opportunity to increase the stiffness of how I'm attaching to it. So why not? So I'm gonna loosely align these fasteners with this build, get the thread started here. And then we do include this nice stubby screwdriver here for tightening those down. Now that I have my bridge plate here, I can install my rods easily and get things lined up for lens control motors. One rod installed. And now by using these flags here, or these adjustment screws, I can make sure that those rods are securely installed into the bridge plate. This gives me great access to the bottom side of the payload here for attaching lens control motors, any other lens support, or in the case that I was using a matte box that wasn't a clip-on like I'm using here, like an Arri LMB, you could also attach that to the end of the rails here. So I'm gonna grab my 3 lens control motors from my Titan transport case and get them installed onto the rods. The MotoCrane lens control motors come pre-installed with 19 to 15 millimeter bushings in them. In this case, where we're using full 19 millimeter size rods, we can just loosen this clamp and then push that bushing through, and we'll set this aside. So now the first lens control motor that I'm gonna be putting on is gonna be on the iris, which is the closest to the camera. So I'm gonna open up that clamp and then push it onto the rod, slide it all the way back, and then get it positioned onto the iris ring here. And I'll slide this around so you can see what I'm doing. I won't have as good of a view here, but we're just gonna get that installed and then tighten down the rod clamp here. Make sure I have good engagement on that rotary function of the lens there. And now there's a few different schools of thought. I'm of the thinking that you should alternate the sides that the lens control motors are on, so that one rod is not constantly being twisted by all of the motors. So for the next one, I'm going to install the next lens control motor onto this rod right here, and that's gonna be my zoom function for this lens. Again, I'm loosening the shaft collar, removing that 15 millimeter bushing, setting it aside, and then I'm gonna install this onto the vacant 19 millimeter rod. Make sure I have good engagement. Just applying a little bit of force here into the gear of the lens itself. Just make sure I have good engagement. So I'm not gonna add my 3rd lens control motor yet. We're actually gonna be adding lens support here underneath this part of the lens. You can see that there's a threaded support section for the lens, and we're gonna add lens support to make sure that we don't have any cantilevered or unsupported mass coming off of the rods here. So I have a part from Wooden Camera. This is a pretty common part that you can get from a lot of different manufacturers that make accessories for camera packages. And we're gonna install that onto the rods near that support. And then we're gonna add a lens support pin right through the bottom here. Push that through here and thread it right into the bottom of the lens there. And then finally tighten the lens support itself down to the rods there. So now we're gonna install our 3rd lens control motor, just the same as before, just loosening up the shaft collar, pushing this out through, and we're gonna set that 15 millimeter bushing aside. Quick note about our lens control motors, this is a swappable hub. So if you find that your lens control motor benefits from the gear being on the other side, you can just pull that right out, push it back in, and have more access depending on which side favors the lens control ring that you're trying to target. So now that we have all 3 lens control motors attached to the payload as well as lens support, we're gonna attach our camera top rail. This goes on the top of the payload, and this is giving us another point of contact. So I like to first make sure that there is a plane from that top point on the camera to where I'm gonna also attach it onto the lens. If you, for whatever reason, don't have this option on your lens, it's not a deal breaker. This is just an optimum setup, and it's gonna help us get the best tuning out of the head. We have a nice level plane here, and I'll point this towards the camera so you can see how that top rail is making nice flush contact here with the camera as well as the lens. So before I put that on, I'm gonna go back into my hardware bag and grab 2 flathead 1/4-20 screws. So I got one of my 1/4-20 flathead screws here. I'm gonna put this into roughly the slot where it's gonna make contact with the camera. I have a separate tool, which is for our English fasteners here. And now I'm going to attach it to the payload. And then grab my second screw and attach it into my upper lens support there. So we've got our payload now built, complete with our bridge plate, 19mm rods, 3 lens control motors, lens support, as well as the camera top lock rail. And now we're gonna get Titan mounted onto its Mitchell base so that we can get this installed and balanced. So we've got our payload ready to get mounted into Titan. Time to set it up onto a support structure, as well as building out our operator station. So for this Mitchell base here, I'm gonna start by attaching my male Mitchell adapter to the top of the Titan pan housing, and then I'm gonna hoist it and get it mounted into place and attach it with the male Mitchell nut. So with Titan mounted to our Mitchell base here, I'm gonna unlock the roll and tilt axes and then adjust the cage so it's ready to accept our payload. Before I make changes to my vertical adjustment on the tilt cage here, I'm going to unlock these knobs right here. You'll see this knob is common throughout the design of Titan for all of the functionality for balancing and securing something in place. This is different from an axis lock here, which toggles on or off. Because the vertical tilt adjustment gets pushed all the way up for stowing into the transport case, we move it down to a more neutral position. I have it aligned with the top of the 11 mark here. There are numerical readouts here to make sure that the cage is not adjusted in an oblong or out of square way. So you can make sure as you're adjusting that it does land in a level and square position. So now with it roughly in a neutral position, I'm going to lock my tilt knobs down, and then I'm going to tilt the camera cage back 90 degrees so I can attach the airy dovetail. I'm going to release the tilt lock here, tilt it back 90 degrees, and that gives me access to the dovetail base bar here. And this, you can see, will adjust side to side so I can get access to these slots for mounting the dovetail. Now, on the standard airy dovetail that's included with Titan, there is a safety plunger at the front of the dovetail to make sure that the payload doesn't slide off. So this is the side that you're going to be putting the payload on and off from. Then there's also a hard stop set screw at the back. So you want to make sure that this is going to be pointed towards the front or the camera lens when you're getting it installed onto the base bar of Titan. We're going to just make sure that we have this loosely aligned, installing up to 4 screws in these slots based on where you want this to live. It's important to note that typically a dovetail is going to live a little bit more rearward on your payload build, and that's because of where the bridge plate attaches to the dovetail itself. If you were to attach your dovetail up in, say, this position up here, you're not going to be able to slide the payload back far enough to achieve tilt balance. So typically, we're going to bias that dovetail closer to a position like this, where we have more room towards the rear, where we're going to have more mass of the lens off the front of it. So this is about the position that I'm going to install the dovetail in. Because this is a slotted interface, you also have the freedom to mount third-party dovetails to this base bar as well. In the event that you have an extra long payload or one that you particularly like, something that's proprietary, you should be able to mount anything with a 1/4-20 here on the bottom of this base bar. So very friendly to other third-party camera mounting ecosystems as well. With my dovetail mounted, I'm going to slide this to the center to a more neutral position to make sure I can get my payload on. I'm going to lock down my side-to-side roll balance knobs right here. And then I'm gonna unlock tilt and put this back into a neutral position so I can get my payload installed into Titan. So I'm gonna go grab my payload and we're gonna slide it in. So I've got my payload that we built before. We've got the bridge plate installed on the bottom, so just like any other airy dovetail system, I'm gonna hoist this up and then slide it onto the dovetail. So with the payload installed onto the dovetail, I'm going to attach the top rail to the crossbar on Titan. There is a clip that's included with all Titans, and this is just to secure this top adjustment slide in place during transport so it's not rattling around. You want to remove this and just set it aside during use. So I'm going to take the sliding piece of the camera top rail and slide it in until it is aligned with the crossbar, and then do the same thing here with the crossbar to the camera top rail. So now with the two sliding pieces loosely aligned, I'm going to loosen the crossbar and bring it down to the payload until I see the thread making contact with the top rail, and then use my crossbar lock knob at the top to engage with the top rail on the camera. So I'm just attaching these two pieces together. You can see as I'm locking this down, the crossbar is going to move down the uprights of the cage until it's firmly in position and secured to the payload, and then I'm going to lock the crossbar down to the uprights using these knobs here. Now, if anything needs to get added to the payload, now is a good time to do that before we get into balancing. In this case here, I'm going to be adding a 6x6 mat box for this lens, as well as cables for my lens control motors, power connection for the camera, as well as SDI connections for video pass-through. So I've got 3 lens control motor cables, a power cable for the camera, as well as an SDI cable. For installing these, I'm going to roll the camera 90 degrees so you can see where we're gonna be attaching these to on the IMU housing of the camera cage. This part right here rotates and moves with the payload. So anything that gets attached from the payload to this doesn't move relative to each other. So there's not gonna be any cable snags or anything like that. So you can see when I move this, it stays with the payload like that. And I'm just gonna adjust that so we get a better view for what I'm attaching to. So on the bottom here, we have our focus, iris, and zoom ports for our motors, as well as a cam port if this were a DSMC2 body or a compatible body with our camera control protocol. We'd be plugging in at this port here. And then just above, we have our 12G SDI port where we're gonna be tapping the video pass-through into. And then if I rotate a little bit further, you'll see where we have all of our power options for providing camera and accessory power. We have 150 watts of regulated 14.4 volts in the form of P-tap or D-tap right there. And then we also have 26 volts regulated for 3-pin XLR. This is airy polarity, so if you need to have a swap cable for a Panavision camera, make sure you're going from airy polarity to Panavision. But this connector is airy polarity. So while we're here, I'm gonna add my power cable for the camera. So I'm gonna go D-tap in and then plug that right into the back of the camera here. And that's the only accessory that I have here that I'm gonna be powering. I do, of course, have room for putting a V-mount battery on this build. I'm not gonna do that, but we could also add that right now as well if we were gonna be powering camera off of a V-mount or a gold mount battery. And now with this rotated, I'm gonna install my lens control motor cables to my focus, iris, and zoom channels right here. This is not a proprietary cable. If you have a 7-pin LEMO cable that you use for Preston, Hadeen, Red Rock, any of those motors, those cables will also work in this application as well. And then lastly, I'm going to be adding our SDI cable from the SDI output on the camera up to the input here for video pass-through through Titan slip rings. So now I have all of the cabled connections installed from the payload into Titan. That includes our 3 lens control motors, power, as well as video signal. The last thing that we're gonna do is add a mat box before we get into balancing of the payload. So with my mat box installed and everything else attached to the payload, I'm ready to start balancing. Now, the first thing that I want to do is adjust the depth. So for the tilt depth, this is going to be achieved by sliding the camera payload on the airy dovetail, as well as the camera top lock rail. So I'm going to loosen the top lock rail first, as well as loosen my bridge plate onto the dovetail. And because I have my safety plungers installed, I know that the camera can't just fall right out of the dovetail. But of course, I want to always keep a hand on the payload right now during balancing to make sure it's not going to get unwieldy on me. So with my hand on the payload here, I'm going to unlock tilt. And I can see that it's very front heavy right now. So I'm going to slide the payload back until it doesn't want to drop forward like this. Good. So at this point here, we're loosely balanced, and I'm gonna just kind of disturb the camera a little bit to see if it wants to still go in any direction here. It's still just a tad bit back heavy, so I'm just gonna push it a little bit more, and that looks great. So I'm gonna lock this down. So now with the tilt depth balanced, I'm going to adjust the tilt height, and I do that by unlocking tilt, and I'm going to tilt the camera all the way back and see if it's bottom heavy or top heavy. Now with it in this position, we can see that the payload is bottom heavy and it needs to be adjusted that way along the tilt axis. So easiest way to do that, lock my tilt axis here, and then I'm gonna get in a position where I'm gonna adjust these balance adjustments here. I'm gonna do that by first unlocking tilt, just like I did before, to get the cage into a more neutral position when I was unpacking, and then adjust these balance knobs. I'm turning them in the same direction, and I'm making sure that the adjustment that I make is the same on both sides. I don't want my cage to get out of square. And we'll do a small adjustment here, and just the same as before, I'm gonna have my hand on the payload and then unlock the tilt axis and see how I'm looking. Much better, still a little bottom heavy. So with it live like this, it is loose. I'm going to simply adjust the payload more until there's no detectable imbalance vertically on tilt. And this looks pretty good. I'm just gonna do one last check to make sure that the adjustment was made equally on both sides. I think this side can go a little bit more, and then we're gonna lock this down. So with those two tilt balance adjustments made, I should be able to orient the payload anywhere about the tilt axis, and it shouldn't creep or drift or fall. The next step of balancing is gonna be my roll side to side balance. And to do this, I'm going to lock the tilt axis first so that that is not unwieldy and unmanageable during this process. And I'm gonna unlock the roll axis. So this is gonna be sliding the payload side to side to make sure that the roll axis is not falling to the left or to the right. Making sure I'm supporting the payload, I'm gonna unlock the roll axis, and I can see that it's wanting to fall towards me or to this side. On the bottom here, you saw how I loosened those knobs to install the airy dovetail. I'm gonna loosen those same knobs as well, but this time I'm gonna simply slide the payload back and forth. And I'm just gonna push the dovetail from the bottom a little bit to make a small adjustment that way. I'm gonna unlock my roll arm to see if I need more. It does look like I need a little bit more, so I'm gonna push it more. I'm going to lock my base bar knobs down as well as my camera top lock rail. And now the payload is secure here, and it's balanced along both tilt and roll axes. So proof of this is if I can move the payload on roll and tilt and it stays in any position. So let's test that really quick. I like to deflect both axes about 45 degrees. You can see it staying in that position, which means that balance is at least not going to be falling to any side under just the weight of the camera. So that's looking pretty good. So I've returned the tilt and the roll axis to their home position, and the last balance I'm gonna do is along the pan axis. Now, in a situation like this, where we're on a Mitchell base that can't be easily deflected, it's a little bit more difficult. I have weight on the bottom of this base, but I'm gonna remove that and just tilt the Mitchell base a little bit so that I can see if there's any imbalance along the pan axis specifically. I'm gonna unlock that. Just by doing a little bit of adjustment here or pulling this towards me a little bit, I should be able to see, and you can see that it is a little bit front heavy there. So again, I'll repeat that. I'm just using the tripod here. I can even grab the Titan carry handle and just bring it a little bit towards me, and we can see that it is front heavy right there. If you're mounting Titan to a support structure that doesn't have the ability to articulate along the pan axis, like a telescoping crane that has a self-leveling head, it may be best to do a payload build on a set of sticks like this so that you can deflect it that way. Otherwise, you can use a U-joint or a dampener, something like that, to be able to deflect the head along the pan axis and detect and fix any imbalance. So I know that this build is a little bit front heavy, so I'm going to loosen these pan axis locks. 1, 2, 3, 4, and then use the pan balance adjust knob here to push the whole pan axis back. So I'm gonna rotate that this way, and you'll be able to see this sliding. And I'll just do a little bit of an adjustment here, maybe 5-6 millimeters, and then test again. Still front heavy, so I'm gonna keep making that adjustment. Retest balance. Looking pretty good. Make sure all 4 of my pan balance knobs are locked down. So we have a rigid connection through the spine here. And now we're all balanced. So at this stage, we have our payload installed onto Titan. All 3 axes have been balanced and we're ready to build our operator station so that we can eventually get everything connected and turn it on. So in this section, we're going to be building out our operator station in its most full capacity with the controller, battle station, and wheels. If for your application, you're using the Titan controller on its own, on your lap, you can probably skip ahead to this part to where we're installing the input modules, but we're going to go through that full build out of all of the battle station components and getting a fully featured operator station built onto this Mitchell base here. So to begin, we're going to grab our battle station and mounting components out of the Titan wheels case and get the spacers installed onto the bottom of the battle station. With those spacers installed, you can add the male Mitchell nut, then we'll get that installed onto our Mitchell base. And once you have the spacers installed, you can add the male Mitchell, and we'll remove the Mitchell nut so that we can install it onto our Mitchell base. So now that we have the battle station mounted to this Mitchell base, we're ready to add our controller. The first thing that we're going to do is add the battle station brackets to the controller itself so that it can bolt right up to these rosettes on the battle station. So with those brackets installed onto the back of the controller, I like to lay the controller flat and position it over those brackets here like that. And I first start, since I'm right-handed, with my right hand, and I get one side loosely threaded. Then I change sides with my hand, and I get the other side installed as well. Now with the Titan controller fresh out of the transport case, there's no input modules installed yet. So I'm gonna put those in right now. And for my preference, I'm gonna add the focus wheel to the left-hand side and the 2-axis joystick to the right-hand side. So an awesome aspect of the Titan controller is how easy these input modules are to install. You can see that there's automatic connectors on the bottom of them, which go towards you during install. And all you need to do to install them is to drop them into those spots and make sure they're fully seated in place. Do that for that one and the focus knob, and then just fasten down those 4 screws and you're ready to go. If you are gonna be using wheels, now is the time to add those to the front rosettes here on the battle station. I'm gonna set up all 3 modules and get those connected as well. Each Titan wheel module can be assigned to any axis, so when you're setting it up on the battle station, you can choose any of these positions based on your preference now just for where the wheel needs to go. We'll assign them to each particular axis later on during setup. So in this case, I'm gonna mount a wheel here, 90 degrees for pan, and then tilt, and then roll off to the side for adjustment. So with my Titan wheel modules installed onto the battle station, I'm gonna get them connected to the Titan controller via the auxiliary COM port at the top. Within the Titan wheels case, you'll see that there are 2 different lengths of auxiliary COM cables, a long one and a short one. We're going to use a longer cable to go from this port down to the first wheel in the chain, and then we can use that shorter one to just daisy chain the additional 2 wheels together. Does not matter what order you go in, they all get connected to the CAN bus the same, and then we assign them later on in the controller. So connect them based on whatever is most convenient for cable routing and for your application. So I'm going to start by using my long auxiliary COM cable and attach one side to the Titan controller. I'm going to leave that there for a second because I want to show you on the back of a Titan wheel module. So from the Titan controller, I'm going to plug into either of the auxiliary COM ports on the back of the wheel. These are both on the CAN bus for communication for all of the wheels, so you don't have to plug into either one, whichever is better for how you want to daisy chain and route cables. And then I have 2 more short cables right here that I'm going to use to daisy chain from the first wheel in my link to the second and the third. Great, so I have all 3 Titan wheels connected, daisy chained off of the original auxiliary COM port from the Titan controller, and now ready to start connecting other cables in the chain. So next up, we're going to get our controller connected to Titan. In a hardwired application, we're going to be connecting a COM cable from this port here on the top of the controller to the COM port on Titan. You can also operate wirelessly. So in the event that you're operating wirelessly, now would be the time to install your 2 antenna into the radio module on both the controller as well as Titan. So to install these antennas, they're simple SMA connections. You just thread them on. and space them roughly at 45 degrees from each other. It's important to note that while this will accept any SMA antenna, you do want to make sure that the antenna itself is matched for the frequency of the radio, in this case at 2.4 gigahertz. So if you're using your own antennas or you lose the ones included with Titan, make sure you replace them with factory units from us or with units that are for the 2.4 gigahertz frequency. Installing your SMA antenna onto the Titan pan housing is just the same as the Titan controller. The radio modules are actually the same, and we'll just make sure that that's installed and out of the way for the rotation of pan, and making sure that we have clearance here for those antennas. For our demo here today, we're going to be using hardwired controls. So we're going to connect a COM cable to the COM port of the Titan controller and then to the COM port of the Titan pan housing. Within the Titan Ultimate bundle, we do include two length options for both COM and power cables, 25 feet and 50 feet. This is a 25-foot unit, but in the event that you were operating much farther away, we do include a 50-foot cable for that as well. Next, we're going to connect Titan to the Titan battery. And it's important to note that you want to first connect the Titan side of the cable first, and then finally to the battery itself. And that's because the battery has what's called an anti-spark connector on it. So it's a sort of a safe start connector that makes sure that you don't arc anything during install. So this is a Titan battery. It is 48 volts nominal, and it's an 18 amp hour unit. With the Titan Ultimate bundle, you get 4 of these plus 4 chargers. So plenty of juice to run Titan for multiple days, even with camera power drawing from the gimbal itself. And you have on the battery a charger port as well as the output port. This is called a QS8 connector. And again, this is that anti-spark connector that we want to connect last in the chain. This is the safest way to connect the battery. So we're now at a point where our payload is fully installed into Titan. We're balanced. We got our controller set up with our operating station. All the cable connections have been made and ready to power on. So we turn Titan on by using the on-off button on the pan housing. We'll press and hold that for 2 seconds, and then we'll see the bright green power LED turn on, telling us that power has been turned on. There will be a little bit of a delay as the system boots up, and then you'll get a blue COM LED, which means that all the communication has been established within Titan. Once you see those 2 LEDs, you can turn on your controller using the on-off switch on the controller. So before we do a deep dive into the controller, let's do a quick walkthrough of how the user interface is laid out and how to navigate. We come to a home screen here where we have 8 of our menu options where we can configure various settings within Titan. On the top left of the controller, we have an adjustment knob for the speed of pan, tilt, roll, and zoom, as well as a record button in the event that we have a camera connected and configured through the camera protocol on the Titan controller. Of course, we have our on-off switch, as well as our motors on-off switch, and the ability to quickly invert the tilt direction or change it from standard to inverted. And then we have some user assignable functions here, user 3, user 4. On both sides, we have these rockers here as well, or single axis joysticks for controlling various functions. We installed a 2-axis joystick here. We have our focus wheel installed over on this side. And then we have this encoder here that allows us to change values and select values within the interface. We'll go through how we use that in a second. We have a permanent home button that will always bring you back to this screen. So no matter where you go in the interface, you can always get back home quickly. Over on the left-hand side here, we have a status button. So this would display any errors or warnings that are present in the system. If something has been exceeded in terms of maybe power or current or voltage or something like that, all the onboard diagnostics with Titan will tell us if there's anything that we need to be aware of. And then at the bottom here, we have user 1 and 2, which are user assignable buttons for hotkeys like return to horizon or level roll or center the pan axis. These are buttons that will continue to gain functionality as we add more firmware features for things that these can be assigned to. So to start off, we're going to do some basic channel mapping to get the inputs set up for how we have this set up here. First, we're going to do joystick, and then we'll show how we do wheels channel assignment. So for assigning axes to the joystick, we're going to go into System, and then to Channel Mapping, and you can see we get a updated view of whatever is connected to the controller. So these input modules are smart, or they have identification on them, so the controller knows what's assigned. In the event that there was 2 joysticks installed, we would see whatever is available with whatever input modules we have installed. So the controller knows what's installed into it and what can get assigned to it. In this case here, we have this 2-axis joystick. So if I wanted a typical configuration of pan and tilt, I could just assign pan to that channel 1, which is my side to side, and then tilt, which is my up and down here, and then confirm that. So it's as easy as that. In the event that you had a profile that you wanted to store, you can save that here. So let's say that you have 2 operators that have the same physical configuration of the controller, but you like things assigned differently. You can save any user configurable profile right here to that aspect of the controller. And then in the case of my focus knob over here, it's already assigned to channel 7, which is the focus function here. And again, that's going to be the rotary function of this knob right here. So with some basic channel assignment here, I'm ready to get into FIZ configuration. I want to make sure that my lens control is all squared away and tested before I get into operation of the head. And to do that, I'm going to go into my FIZ page here. And this first page is going to let me adjust things like speed, smoothing, and the direction of the motor for how each of those 3 axes are moving. It's also going to give me the status of each of the 3 axes and tell me which models I have configured to set up. We have compatibility with MotoCrane's lens control motors, as well as the Hedin M26s, as well as the Preston DM2s. And of course, that library will increase throughout future firmware updates as we add more lenses or other compatible motors become available with our driver. So we're going to go to the configure page here and make sure that the connected models of lens control motors are correct for what we have connected. We have all 3 MotoCrane motors, but let's say that we had a Preston DM2. We could configure that down there and assign that. I'm going to bring this back to MotoCrane. And then one further step in, these are presets for different lenses. So specifically what we're looking at here is for the barrel of the lens, is that a looser or a stiffer lens in terms of its rotation? This is an Angenieux Optimo 17-80. It's a pretty free moving, pretty loose moving lens. So I'm just going to hit load preset on the loose side, and that's going to change my configuration values here so that I'm not overdriving the lens or applying too much torque, but not so soft that it's not going to be driving the lens for a successful calibration. So these configuration settings are really for successful calibration of the lens when we get to that in just a second. So again, I just hit loose on my preset, make sure that my models are correct for the motors, and then I'm going to go back, and at this point here, I'm ready to do a focus iris zoom calibration. So I'm going to press start. I'm going to make sure all 3 axes are moving. It'll do one direction in all 3 axes, and then once it's done, it'll do the other direction on all 3 axes as well. Now, in the event of a calibration fault, like I've experienced here, I'm going to actually increase the calibration power on that specific axis. So I can go to Configure and go to Calibration Power here. In this case, I had a calibration fault on focus. And that just means that that particular axis needs more power to calibrate successfully. So I'm going to bring that up to, say, 150, and we're going to run that calibration again. We'll go back to Return, and I'm going to hit Calibration, and we'll let it run. And with that change, we have a successful calibration on all 3 axes. I can now jog each of the 3 axes to make sure that we have our full range of those rotary functions on the lens, so full zoom, as well as full range on focus, and then, of course, our iris as well. With focus, iris, and zoom calibrated, we're ready to get into basic tuning and operation of the head. So we're going to just go to our tuning page here, and we're going to see some values that may be familiar to you based on what stabilized head system you're coming from with Titan. So we have controls for pan, tilt, and roll. And then the 4 controls that we have for tuning are power, stiffness, control, and LPF, which is our low pass filter. So let's walk through each of these tuning values to make sure that we have an understanding of what they all do. We're gonna start with stiffness, and stiffness is the sort of the strength or how hard the head is trying to maintain the current target angle. When it's too low, you're gonna see poor stabilization. You're gonna see the head kind of oscillate back and forth, and when it is too high, you're gonna see it overshoot a certain target position. Now, control helps us to slow down or dampen the response to changes in target angle. So control, we start to increase when we're seeing some high frequency vibrations in the stabilization, especially important for tracking vehicle work. And then LPF is a value that starts to taper off the power of the stabilization loop at certain frequencies. So in the case of roll right now, the stabilization gain starts to decrease at 40 hertz or 40 times per second. So this helps cut out resonance and a bunch of sort of vibration noise and sounds when we're operating the head. And then power over here is actually a gain or a multiplier that is associated with the stiffness and control values. So power is convenient because when you turn power down, you're actually turning stiffness and control down together. So like, let's say that you have a certain axis that is humming or buzzing or performing poorly or producing some symptom you don't like. Instead of trying to figure out if stiffness or control or LPF need to come down, you can just pull power down on that axis and then start to bring the stiffness and control values back up individually to regain whatever performance you're looking for out of that axis. So anytime that you're really troubleshooting tuning on a particular axis, you first adjust power up or down, whether it's looking sloppy or it's buzzing or producing oscillations. And then LPF is usually associated with just the size of the camera build. So these default values here tend to perform pretty well. And at the top of the tuning page, we have our GPS assist on or off. And GPS assist is a system that we've built that provides really excellent results for our tracking vehicle customers, especially when you are outdoors, you're doing sustained lateral acceleration, going around a corner or on a racetrack. GPS assist is great for that. For indoor studio applications where GPS reception is poor and that assist might provide actually worse performance, we give you the option to turn that off so that you don't have any symptoms associated with bad satellite reception. Now, the first thing that we do to establish some baseline tuning values is we go into presets and we determine which size camera package is most appropriate for our payload. So for this payload here, we would consider this a medium-sized payload. It's definitely not the largest, and it could certainly be smaller in the event that we had a prime or something on this camera body. We do have a handy chart in the operation manual that helps to distinguish between small, medium, and large. Check that out. That's helpful for determining what your baseline preset values should be. So we're gonna load the medium preset in here. And while I'm in this page, I wanna show you a cool feature that we have, which is saving different tuning presets. So at the bottom, you see custom 1 and 2. And then we also have a second page here for another 5 custom values that can be stored. So when you have payloads really dialed in, you can save those tuning values, and then later on, if you have a camera change or something like that, that camera package comes back to you. You can load those tuning values and not have to go through the process of tuning again. So convenient way to store popular, if you're always using a Premista and a certain camera body, you can store that right here and then make note of, custom 5 is the preset that we stored it for that particular camera package. We're gonna use our medium preset and then go back to tuning and just make note of those tuning values. And then we're ready to turn on our motors. When Titan turns on, it is a safe start system where when power is applied, the motors do not start automatically. You have to arm the motors either through the controller or on the gimbal itself. And I'll show you that here on the back. There's a dedicated arm motors button right here. It's upside down right now because the gimbal is overslung, but we can press arm and then hit confirm, and our motors are armed. Now, that doesn't mean that the motors are turned on, but it means that we now have the ability to turn them on and off. I want to make sure that all my axis locks are off. And again, make sure that I'm all balanced. Nothing has changed on this payload, so there's no reason why I wouldn't be balanced. You can see that when I armed the motors on the spine, we did get this icon at the top where it says armed next to motors. they are still off because my motor's switch is off here. So with motors armed, we have the ability to turn them on or off. And again, this is for safety of assistants or anyone that's going to be walking around the head or anything like that. It also gives the ability for an AC or someone to come up to the head and disarm the motors, make a change or do something here, and then arm the motors again and leave it how it was. So it's a helpful safety option. So in the event that Titan is not accessible and you need to arm the motors, there's functionality to override that through the controller. We're gonna go to System, press Overrides, and then press Motor Arm. We can also remotely power cycle the head on and off in the event that that were to need to happen. Let's say you have Titan mounted remotely and it's time to go to lunch and you want to turn everything off. You can remotely power the whole head off and also turn it back on, provided that power is still connected. So we already had our motors armed. So I disarmed them and now we can arm them again. And you can see that we got that icon there. So 2 different ways to arm your motors, which gives you the ability to turn them on or off. So with a tuning preset selected and motors armed, we can now turn the motors on. So when we do that on the controller, in the event that the roll axis was off level, it will level roll. It will leave tilt and pan wherever it was, and I'll demonstrate that here. So if we have this over here, and we turn motors on, it will find its horizon and it will recenter anytime that we turn motors on and off. A couple of quick hotkeys or shortcuts that are very popular for associating with these user 1 and 2 buttons are things like leveling roll, or we can do level horizon, which levels both roll and tilt. So if we go to our channel mapping here and we look at, say, user 2, we can look at all of the functions that are available for a shortcut or a hotkey for that. So in the case of my application, I like to have a level horizon. And let's say that I'm rolled and tilted up. When I press that, it's gonna bring everything back down. So a lot of different functionality and customization you can do within channel mapping here for your application and your preference for operation. Now we're gonna take a look at the control page where you can adjust the settings to make sure the joystick feels how you want it as an operator. Smoothing, deadband, and expo are pretty common configurations that any joystick would have associated with them. Smoothing, of course, is how soft the start and the stop is. Now, if we want those starts and stops to be more smooth or a bit more organic, bring that up to a little bit higher of a value. And we'll still have responsiveness at this kind of value, but it won't have sort of the jitter that you might get, especially in a tracking vehicle where you're trying to smooth something out. Deadband is how wide the joystick will have to move or how far the joystick has to move to start commanding a position. So if you have a joystick value that is very, very high, say 55, somewhere in here, you're gonna have to start moving the joystick quite a bit to start seeing the head move. So typically we see values around 10 or below to make sure that we still have the responsiveness that we want. When you go down to 0, sometimes there's the risk of seeing joystick drift because maybe the joystick is actually reading a -1 or -2 value. So we'd like to have a little bit of room around there to not have incorrect axis control coming from the joystick. And then expo is how strong of an exponential curve do you want associated with the axis? So with expo values that are very, very high, like this, the moves are going to become exponentially greater as you move the joystick further along. So the first 50 to maybe 75% of the joystick is going to be only very small moves, but at the end, you're going to get a lot of action at the end of that joystick. If you bring it down to 0, that is a linear output, so you have more of a straight or a linear relationship between the joystick position and what the axis is doing. This is going to feel a lot faster at low speeds or at low joystick input. High expo is a lot more beneficial when you're on longer lenses, where you're trying to punch in and kind of make smaller adjustments with the joystick, but you still want to have the ability to really crank on it and have an axis, be able to whip pan or something like that. I tend to be around 50 on expo, and that gives me the control that I need to sort of start and stop, within a range and aim, point the camera how I want it to. And of course, we have all 3 of those settings for all 3 of the axes: pan, tilt, as well as roll. Now, for a lot of users, wheels is going to be your preferred way to control the system, and setup is simple. With however many wheels you want configured for your application, always pan and tilt, maybe you want roll as well. You're gonna go right into your wheels setting, and you see we have a spot for pan, tilt, and roll. All 3 wheels are blinking, meaning that none of them have been assigned, and we can see that as well in our status boxes for each of those 3 axes. So to assign, I just click the assign button on an axis, and it's gonna instruct me to press the status button on the desired wheel module. So in this case, I want pan over here, and we have that assigned. I'm gonna do that same process with the other 2, and now we're good to go. Solid green means that you have assigned that wheel to an axis. Let's say that I messed it up or I want to change something. I can just unassign whichever one I want. In this case, I'm going to unassign roll. And you can see now it becomes available for reassignment somewhere else. I'm going to assign that back. Now, as far as speed and mechanical drag on the wheels, those happen local to the wheel right here. So for adjusting speed of this wheel, I don't do that up here. Again, that's just for joystick. If I want this wheel to have a higher, what we call a gear ratio or higher speed, we do that adjustment right there. And then we also have a mechanical drag adjustment for the wheel as well. So if you're an operator that likes to have a little bit of resistance on the wheel, you can dial that in here on the drag and have a little bit of drag here. Or you can really free it up and have the wheel spin with no drag at all. Within the wheels configuration, you can also change the wheel direction or invert the way that it controls the axis, and then you can also apply smoothing. So we have a very low smoothing threshold on this. We typically run values around 20 or 30, and that just makes sure that you don't have overshoot on the wheel since you are commanding an absolute position. So wheel smoothing values of say 20 to 40 are still very responsive, especially depending on the focal length that you're shooting. It just helps the axis itself move more smoothly and not have overshoot or any kind of jitter within the command that's coming off of the wheel. Wheels are pretty easy to move. I'm rubbish at wheels. I don't know how to use these things. I'm a joystick person, but I'm told these ones feel pretty damn great, and looking forward to what you shoot with them. Another handy function here is in the event that you want to walk away as an operator and keep everything on but not have someone mess with the wheels or change anything, you can just press status on all 3, and then that makes the wheels safe to be around. No one's going to come up and move anything from the shop. So another really handy feature that we built into the Titan user interface is the monitor functionality. And within this first page here, which we call Diagnostics, you can see the position of wheels, as well as all the values that are on the controller. So where all the various knobs and channel inputs are. And then on the bottom here, you're able to see things like motor temperature, motor current, encoder feedback, your motor driver temperature, and then also IMU angle, or what's being calculated for that axis. So this is helpful if you're trying to scrutinize kind of one particular aspect of something, maybe a joystick that's drifting or a motor that is warm. You're able to look here and get that information. And another really handy feature within Monitor is our scope functionality. This lets you measure both gyro and motor data for any of the 3 axes. So anytime that you might have an axis that's not performing how you want and you can't figure out which one it is, you could turn on gyro for all 3, and you'd be able to see a particular shake or a bump that you then want to do tuning on. So in this case here, I'm just going to shake it along the pan axis, and we can see that blue line on the controller. Same thing if I did that for tilt, we're able to see that, as well as roll, and that's our green one there. So super handy if you have a head that maybe is buzzing or a tuning issue and it's not close to you and you can't really feel it. You can use scope to dive in and really see what's happening on the gyro as well as motor power that's being commanded to the axis. As soon as we launched Titan, we had a lot of people asking about any kind of shake generator that was built into the head. So within about a month, we had gone from no shake generator to what I think is probably the best one in the world right now, as far as the ability to make it exactly what you want. And the fact that it's built into the head and not a control system, which is an important distinction. So for our shake generator, it's really easy to use. We're gonna go into the shake page, and you have the ability to change the character of the shake for all 3 axes, as well as turn the effect on or off. And then at the top of this page, you have the ability to control the overall level of the shake generation as well. So in this case here, I want to have a tilt shake. Tilt shake is usually the one that's most closely associated with speed. It's the one that I've seen the most commonly used in commercial applications by famous directors that have a look associated with that awesome shake look. Typically, we're seeing that high frequency along the tilt axis. To make that happen, we want to make sure that we have all three of these values up high enough to actually produce the look that we're looking for. And let's talk about what each of those things does. So amplitude, this value, the higher it goes, the larger the shake is going to be in degrees. It's actually going to shake the camera more or less. Frequency is how often that shake happens. So lower frequencies are going to have literally a slower shake. Higher frequencies are going to shake faster. So it's basically time versus how much does it actually shake. And then resonance is kind of a bit of a reverb, if you will, at the end of each of those moves. So it makes it feel a little bit less clinical and has more of a realistic look to the shake. So at the top here, we have master levels, and that's gonna turn on shake generator or turn it off based on what we have configured down here for each of the three axes. And then amplitude, this is gonna turn up the overall amplitude of the effect. Again, that's been created down here that we've configured. And then frequency is the same thing there as well. How often is the shake generation happening? And then random helps to add some random mix into those values of amplitude and frequency, and it helps the shake to look more organic and less constant and clinical. So we typically like these values to be around 100 to start actually seeing the effect. So we have our amplitude, frequency, and resonant values up high enough where we're actually gonna see a shake effect. And once we have our motors turned on, we're ready to actually turn the shake generator on as well. So now we can actually see the camera package being, shaken right now. This is using motor power to actually shake the payload up and down. You can hear the motor working, and you can actually kind of hear and see these values at play. So if I bring amplitude down on tilt, we'll see the amplitude of how much it's shaking get reduced. The frequency is still the same. It's actually still shaking just as often, but it is a narrower amplitude. Now, if I bring that up a lot more, we're gonna see a much larger shake. And you can see just at the end of the matte box there how much more it's shaking. So you're gonna adjust these parameters based on your desired effect and also the focal length that you're shooting at. Longer focal lengths, of course, are gonna take way less input to shake that lens more based on that narrower field of view. So it's awesome because you can really experiment with this and make it your own. Just be wary that you are using motor power and battery energy to shake the camera. So you'll probably experience less battery life when you're constantly shaking the camera. You'll also get the motors a little bit more warm. So depending on your application, just be wary that there is a cost for a shake generator, and you're basically consistently running the motors and using that torque and power to shake it around. Another cool shortcut that we've added for shake generator specifically is the ability to toggle it on or off. So if we go into System and Channel Mapping, we can actually assign shaker on or off to a user button and toggle it on or off just by pressing one button. This is great when you're operating and you're really, your eyes are in the monitor. You don't want to have to go through any menu thing. You're on a tracking vehicle, and you want to have the ability to just turn a configured shaker mode on or off with just the touch of a button. So I'm just pressing this on or off, and we can turn that look on or off. So super handy. It makes it much less of a burden when you're not having to go into menus to turn something on or off. Thank you for joining me for this technical walkthrough. This is going to be the first of what I'm sure will be many tutorial videos about MotoCrane Titan and the various accessories and aspects of this stabilization ecosystem. If there's something that you think I could cover more, you still have questions about how to set something up, make sure you get in touch with us by email or leave a comment. This will be, again, the first of many things that we're trying to do to make sure that people are getting the most value out of this powerful stabilization ecosystem. Again, I'm Zach. Thanks for watching.